Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about combinations of capacitors. So capacitors placed in series with each other and placed in parallel with each other. So let's get into that. First of all, we have our circuit symbols for capacitors. This is something worth maybe taking a moment to do. Different elements within circuits have different symbols to represent them in a diagram. For a capacitor, it's a pair of parallel plates like this, because the basic geometry might be a parallel plate capacitor. So when you see this symbol, it means that you have a capacitor within your circuit. There are some other symbols that we will commonly use, like this one right here will mean a resistor. This right here, where there's a thin, tall terminal and then a shorter, fatter one, means that you have a battery. If you have like a triangle with a little line next to it like this would mean a diode. This right here, or sometimes this right here, represents an inductor, and then this right here is the symbol for ground. Sometimes it also just has a triangle like this. Either one of those works for ground. Now again, today we're focusing on the capacitor, and we're looking at series and parallel combinations. So a series combination of capacitors would basically be one, and then the next one, and then the next one, and so on. A parallel combination will look more like this. I've got my capacitor, and then my wire branches down. I have a second capacitor. Maybe it branches down further. Oops. And down here I have a third capacitor, and so on. So this right here would be parallel. The important thing with the parallel is that they branch, you have your elements, and then the branches reconnect. In series, there's no branching. Okay. Now what we want to do with series and parallel combinations is essentially take this combination and say, if we were to replace the combination with a single capacitor that is equivalent, so we could call this an equivalent capacitor, what would the properties of that equivalent capacitor be? Essentially, we need this equivalent capacitor to sort of be indistinguishable from the combination of capacitors if that combination was placed within, let's call it a black box, is usually what it's called, meaning this stuff exists inside of a box like so, and we can see the outside of the box, but we can't see what's inside of the box. But we can connect the box to something else like a battery or a resistor or what have you. And as a result of connecting it, it'll draw some current off the battery. It may have a total voltage drop, may store some total charge, that kind of thing. And so my equivalent capacitor would be, if I don't know what's inside the box, but I could take a single capacitor and replace the box with that capacitor has to behave the same as this box that I don't know what's in it. Okay. Now there are a couple of ways of approaching parallel and series combinations. There's a geometric approach. So the geometric approach looks like this. You have the capacitance C. It's given by epsilon naught times plate area divided by distance separating the two plates. And so the geometric approach is to say, if I were to, and by the way, you can also put a kappa dielectric in them, But the geometric approach says if I were to combine these in parallel or in series, how does that combination affect the sort of total area, total plate area that I have to store stuff on, and how does it affect the total distance between plates, or the equivalent distance between plates? So we could begin by, for example, a parallel connection. And so in a parallel connection, I have a plate here, I have a plate here, and then I branch down here, and I have a plate here, and I have a plate here. And for the sake of argument, let's treat the plates as if they have the same separation distance. So if this right here is D, then these two are also separated by D. But this plate, or this pair of plates, has area A1. This pair of plates has area A2. Now what that does is, it means that you can imagine like taking the two plates and just kind of like linking them together. So if I were to link these two together, I would end up with a pair of plates that have a total area of, or we could call this total area A1 plus A2. Basically, if I take the two plates and I just connect them together side by side like this, then I have this area and I have this area. I put them together, I have the total area is the sum of the two areas. The distance between them remains the same. Okay, so in this simple sketch, by putting these two in parallel, I'm basically adding their areas together. Everything else stays the same. That means that my capacitance should look like C is equal to kappa epsilon naught, we're assuming the same dielectric between them, times A1 over D plus A2 over D. Oops. But this is the same thing as kappa epsilon naught A1 over D plus kappa epsilon naught A2 over D. And this just is capacitor 1's capacitance. This just is capacitor 2 capacitance. And if I add more to this parallel connection, then I would just be adding additional A3, A4, A5, etc. terms. And so that means that my total equivalent capacitance, just from geometry, is C equivalent is equal to C1 plus C2 plus, if I have additional ones. Or in other words, C equivalent is the sum of all of my individual capacitances. Cj, J is an index term, so it's 1, 2, 3, etc. Okay, so that's the geometric way of looking at plates in parallel. Okay, what about if we put them in series? So if I put the two in series, what does that do? So I've got here one set of plates, and so this has some distance separating them. They also have some plate area. Let's say I have another one with the same plate area and maybe a different distance separating them. Okay. Maybe it's even the same distance, just to make life easier for the sake of illustration. Well, if I were to look at how charges go, if I have plus charge here, this one will be minus, and the way that it's minus is that it pulls, or where these electrons come from, is that they're pulled off of this plate. There's a gap between the two plates that you can't have electrons crossing. So each electron on this plate had to come off of this plate. And so that means that this plate will also have a charge of minus over here. Okay, well this is very similar from an electric field perspective to having, something like this. And so my electric field lines, if I'm going to draw them for this combination, I'd have the field lines moving horizontally or pointing horizontally from the first to the second, I'd have an interruption, and then I'd have field lines from the second to the third. Now, how much total charge is being stored? Well, in some sense, I can kind of like neglect this pair of middle plates as being sort of like an interruption in my capacitor. And so I only care about where the field is. And my total charge stored, if this one has charge Q, this one will have charge minus Q. And so again, I have plus Q here, and I have minus Q here. All right, so I basically neglect the portion where there is not an electric field. My effective distance where the electric field exists, therefore, is D1 plus D2. So I've increased my total distance. That increases here in the denominator of the capacitor. The end result is that in order to sort of like add things together, if I did 1 over C, that would be D divided by kappa epsilon naught times area. And so that ends up being D1 divided by kappa epsilon naught area plus D2 over kappa epsilon naught area. But these just are, by definition, 1 over C1 plus 1 over C2. And so my equivalent capacitance, becomes my equivalent capacitance. This is sort of like my equivalent distance. My equivalent capacitance reciprocal is the sum of the reciprocals of the individual capacitances. And I can add more terms as needed. So 1 over C equivalent is the sum of 1 over Cj, summing over J. And this is my series combination. The other one that I did before was my parallel combination. Okay. Is there another way of doing this? Yes. The other way of doing it is to look at how charge and voltage and all these things are behave within a system. So again, if I were to do my series combination, I could, or my series combination or my parallel combination, I could look at what the total charges are and what the total voltage drops are. So my total charge for the series is Q. And so Q is equal to Q1 is equal to Q2 is equal to ... My voltage drop total is actually the sum of the individual voltage drop. All right. So if I wanted to do my total, I could say it like this. But remember that Q is, that a capacitance is given by Q over delta V, which in turn means that the voltage drop is going to be Q divided by C. And so basically the voltage drop for the J capacitor would be Qj, or just simply Q, since all the Q's are equal, divided by Cj. So that is another way of saying like delta V1 is Q over C1 and delta V2 is Q over C2, etc. Okay, so that means that this equation here can now be rewritten as Q divided by C, or C equivalent, is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3 plus etc. And now we divide out a Q from all of these, and you get the same equation that we got before for the series combination. 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3 plus etc. If we turn instead to the parallel combination, then the rule becomes that the voltage drops for each capacitor are actually equal to each of the other capacitors. So we could say something like delta V is delta V1 is delta V2 is delta V3, etc. The charges stored, on the other hand, are going to all be different. But if we were to add them together, Q1 plus Q2 plus Q3 plus Q4, etc., then we would get essentially like Q total. The rationale being that if I am connecting a whole bunch of these capacitors to a common power supply somewhere, that power supply is able to basically send out charge along these connectors to each of these individually. And so one electron being sent off of this to here and one plus charge being sent off of this to here doesn't really affect the number of pluses being sent to here or here or here. And so I'd have like plus Q1 plus Q2 plus Q3, and then the minuses on the other plate. So minus Q1, Q2, and Q3. And again, this is because I can, if I want to put like 5 here, 6 here, and 25 here, I can do that because I can pull 5 plus 6 plus 25, or 36 total, off of this battery and distribute them accordingly. Okay, well, again, using the fact that Q is equal to C times delta V, or in other words, that C is Q over delta V, it follows that the total would be C equivalent times delta V is equal to C1 delta V plus C2 delta V plus C3 delta V plus etc. And so that means that we can divide out a delta V from all of the terms. So like I can divide out a delta V, a delta V, a delta V, and a delta V. And so what I end up getting is C equivalent is C1 plus C2 plus C3 plus etc. Again, same result that I got here in the geometric approach for the parallel case. All right, so we've now seen two methods for getting our answers. Let's do a quick couple examples. So if I have a set of 3 capacitors that have capacitance respectively of 10, 20, and 40 millifarads, and I combine them in parallel, then my equivalent capacitance CEQ would be C1 plus C2 plus C3. And so that is 10 millifarad plus 20 millifarad plus 40 millifarad. And that's relatively straightforward to add. This gives me a total of 70 millifarads. So my equivalent capacitance is 70 millifarads. If they're in series, then I have 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. And so that is 1 over 10 plus 1 over 20 plus 1 over 40 millifarads. So what does that add up to? It actually adds up to 7/40 millifarads. So 7 over 40 millifarad. And that means that my actual equivalent, because this is 1 over C equivalent, my actual equivalent is 40 millifarads divided by 7. And so that ends up being about 5.7 millifarads. Rounds off to about 5.7 millifarads. All right, let's do another quick example. We now have a set of capacitors that are all in combination with each other. If you look, these two right here are in parallel. We could call these, if this is R1, if this is R2, and if this is R3, then this is equivalent to a combination that has R1 in series with another sort of like baby equivalent resistor that I'm going to label R23. Okay, so 1 over R23 should just be R2 plus R3, or in other words, 20 microfarads plus 30 microfarads. And so that's 50 microfarads. Now we can combine these in series with each other. So this gets me an R equivalent of 1 over R1, 1 over R equivalent of 1 over R1 plus 1 over R23. So 1 over R equivalent, using this formula, is 1 over 10 microfarads plus 1 over 50 microfarads. And so that's 6 over 50 microfarads. And that means that my total equivalent resistance is about 8.3 or 8.3 repeating microfarads. All right, so that's a few quick examples, and that's all that I'm going to do in today's video now. So hopefully you've learned something from it, and thanks for watching.